Welcome to the third season of That's So Second Millennium, the Catholic Science podcast where we explore the fascinating borderlands between science and theology through realms of philosophy, human experience, and more.
Welcome back to That's So Second Millennium, episode 132. This is a solo episode coming to you from Wyoming Catholic College, discussing the history of mathematical physics, discussing the methods that have evolved over time, and the external impulses that governed the formation of those methods, and their use from the time of the Greeks all the way out to the time of Galileo in the early 17th century. This is the sort of stuff that made me really enthusiastic to take this job, and I'm enjoying the chance to share it with you. So without further ado, here's the history of mathematical physics from about 500 BC to about 1640. Welcome back to That's So Second Millennium. This is Paul coming to you from the offices of Wyoming Catholic College. And my voice is probably a little different today because I am adjusting to the fact that I have I've gotten hearing aids. And so my voice sounds very loud and strange to myself right now, echoing off the walls of this office. Hopefully it's not noticeable to all of you. It's very noticeable to me, and it's very strange. Today, I'm going to need to do a solo episode today, given scheduling constraints on myself as well as Bill more than anything else. We have some ideas for people we'd like to interview coming up, but we haven't been able to bring those to fruition just yet. So today, actually inspired by the class that I'm teaching here on mathematical methods, actually we call it deductive methods in science here at Wyoming Catholic College. And all students take it because all students take every class here. That's the nature of the curriculum here. We give them a single degree in humanities and the liberal arts and turn them loose upon the world. We try to teach them things that are worth knowing in themselves, and that's, in my case, that's peering into within the walls, underneath the floors, even the structure of the ceiling, so to speak, of this cathedral of a universe that we inhabit, and to try to give them an appreciation for that. And it's difficult. It's very difficult. There's going to be a lot to adapt to in terms of students with very wide range of backgrounds, because more than half of them have been homeschooled, and so there's the delightful, riotous mixture of different. That's the whole point of homeschooling, is that the parents themselves can choose what their students get to learn, and they make different choices. People are inconvenient like that. I think Hilaire Belloc would, with tongue-in-cheek, make that observation. Modern bureaucrats are very dissatisfied with the choices that we individually make, because they're just not tidy. They're just not tidy. And I am not going to make that complaint. I'm just going to observe that I have to do what I can to try to address all of them. So the idea of mathematical physics, of course, we're going to go back to the Greeks, and the figure of Pythagoras, ironically, we recall in the modern world because of Pythagoras' theorem. That's the touchstone. We remember that strange name of the strange fellow from the middle of the first century, the middle of the first millennium BC. But in fact, he and his school were really taken with arithmetic and almost the sacredness of number. I'm not an expert on this. This is actually reaching back to readings that I did many, many years ago. About the history of mathematics and, great theorems in mathematics, I believe was the title of one of these books that I read a number of times back then. And so there was a great crisis at the very outset of the history of mathematics, of Western mathematics as we know it. Of course, there was practical mathematics. There was practical geometry that the Egyptians and the Babylonians, the Sumerians, and so on must have had to have had, that we have, about as soon, if not sooner, than we develop language, for heaven's sake. But nevertheless, obviously there was something with figures like Thales and Pythagoras. Something new had happened. And China and India have their own mathematical histories that I'm not familiar with. Someday I would love to have the chance to learn at least a little bit. But in terms of the Greeks, it starts with them in the first millennium BC. And so early in the history, during the period, Pythagoras has almost a cult. There are people, who follow Pythagoras, revere him almost as a prophet, to my knowledge. And one of his followers develops, the realization of the basic fact that of incommensurability, and many of the early Pythagorean mathematical results depended on the belief that all distances must be commensurable, which in a way means that all geometric lengths must be somehow, in a certain sense, arithmetical. It means we can find, if everything is commensurable, then that means we just need to divide two different lengths finely enough, and we will find a common, what we would now call a greatest common divisor, so to speak. Something that will go evenly into each length, and thereby really, translate the lengths into numbers. I don't want to say reduce the lengths to numbers, although perhaps that's not inappropriate in this context. And you can't, as a matter of fact, as commonsensical as that seems, I just go small enough. Of course I can manage that. But as a matter of fact, you can't do that. And it's as basic as soon as you cross a square with a diagonal, the side and the diagonal of a square are not commensurable. So this very, basic everyday figure contains the seed of, and of course, that's it. It's simply because it's an irrational number, what we would now call an irrational number, which it means much the same thing. We can't construct it as a ratio out of units. We can't break, if we take the side of the square as our unit, we simply can't break that unit down and then reconstruct the diagonal by building it up again, by multiplying it by a certain number. And this was a crisis. This was just an absolute intellectual crisis. I even read that there was a legend that the guy who discovered it was drowned. That's a bad sign. Bad sign. So this in a way seems to have created a lean in Greek mathematics away from arithmetic. Here at the very outset, in the first few generations of people doing what we would call really, serious mathematics. And so from that time on, and especially crystallized in Euclid and Euclid's Elements, we have this heavy lean toward geometry. And of course, so Euclid simply starts out with plane geometry. He does a book on that. He does a book, that weird second book where he discusses gnomons and lines cutting other lines. He has a third book about circles. And so by the fifth book, he's talking about proportions, but he's doing it with these, not messy, but, not very illustrative geometric figures of here's a line and here's another line, and I'm going to talk about their lengths. I'm going to talk about the mean proportional between them in terms like that. But it was the tool that they trusted now. They didn't trust arithmetic anymore. They felt they had to. Geometry was in some sense superior. It had quantities that, that arithmetic couldn't touch. And so there's also, of course, at the same time, this lean toward axiomatic proofs, and this desire for absolute certainty, which it's understandable. If the Pythagoreans had been more rigorous, there was a sense that there was a crisis and a whole bunch of proofs that needed to be redone, and no one likes redoing work. It's very very terrifying to have to redo large amounts of work, as anyone knows who's built something wrong and perhaps covered, put his studs in wrong and covered it with a wall, and then realizes he's going to have to tear that beautiful new wall material out, or at least try to rip it off with doing as little damage as possible, and then try to redo it all from the beginning. Or perhaps he needs to redo the wiring within the wall, something like that. To do that with a massive intellectual project is just as bad, just as nasty. So there's this crisis, and this reach toward axiomatic proofs, and a particular style of axiomatic proofs. And so this is, in the late first millennium, the environment in which people, and by people I mean Archimedes in particular, he was not the only one, but Archimedes stands out far above the crowd in terms of someone trying to do mathematical physics. And he's doing it in this paradigm, not with our modern notation, not with our x's and y's, and also not with the tools that we have of analytic geometry. He's doing it with, now we have this modern, stuffy term of synthetic geometry. But it's simply planes, triangles and rectangles and circles and so forth, and as much solid geometry as we can wrap our heads around, which for Archimedes is a lot, and the rest of his contemporaries not so much, because Archimedes was insanely brilliant. So Archimedes starts to do things. So the text of Archimedes we actually cover in our class is called On Floating Bodies, and that was a trip, encountering that for the first time, because I'm expecting Archimedes to talk about floating objects in a vessel, an everyday vessel of some kind of bucket or something. And instead, in his proposition 2 of this little book, where he starts actually doing physics, there's this diagram that's a semicircle, and I immediately find out that the center O of the semicircle is the center of the Earth. What? So he realizes, in some sense, of course, and I, less than half jokingly with the student said, isn't there this lie or this story that this guy named Isaac Newton quote discovered gravity? I mean, what's this Archimedes doing? He recognizes that the center of the Earth is what things are attracted to, and that the surface of any fluid is a segment of a spherical surface. The surface of any body of fluid is a piece of a sphere whose center is the center of the Earth. How did he have that level of insight? I mean, it's crazy. It's just crazy. And so he starts to prove Euclidean propositions with, the help of a postulate about the behavior of fluid, which, our English translation of it was incredibly messy. And it, contains things like the piece of the fluid that is thrust more drives along the part of the fluid that is thrust the less. And so there's this great uncertainty about exactly what, physical concepts, the precisely defined physical terms that we now have, which in, force, weight, pressure, all of those need to be defined to really understand exactly what Archimedes was getting at. So this piece of work, is just, it contains incredible insight, and in a way it's also very tedious. And so then we go on. So the history, Archimedes, killed by the Romans in the middle of the 2nd century BC. And so this legacy continues on. And then the other side of the physical legacy of the ancients is Aristotle. And Aristotle's reasoning about things in a very, we call qualitative sense. I mean, that is the rap on Aristotle, is that he will put things into categories, and he will think, this is in this box, and then it goes over into this box. And if it's being moved by this thing, it can't be moved by any other, force or impulse or something at the same time, which is radically false. But seems intuitive. And Aristotle being the teacher of the Middle Ages, especially the High Middle Ages, there was a long period where questions like this simply didn't occupy people in the West, and not that many people in Byzantium. And so, when people do start to haul this out, they think about things in Aristotelian terms in the early 2nd millennium. So there's this over, millennium and a half, well over a millennium and a half, almost 2, where this Euclidean paradigm is still current, and that descends all the way down to the early 17th century. And so this week we're reading Galileo. We're reading texts of Galileo, and like Pythagoras, I mentioned earlier, we know for things that, didn't necessarily occupy his time. We also know Galileo in terms of his astronomical work, and arguably he's more influential in terms of his analysis of motion and accelerated motion, and things like that. But Galileo in the 1630s, starting early in his life, around the turn of the century, but on into the 1630s, is still working in this Euclidean paradigm of mathematical physics. He's still drawing these really tedious diagrams. And to be perfectly honest, some of his proofs are kind of shaky. Galileo's a fascinating figure. And it's a privilege to be here and to be reading some of these primary sources and get to know things that I've read in secondary sources. So it's kind of a commonplace in the philosophy of science, in the history of science, to comment that Galileo didn't have the evidence to back up his assertions about the heliocentric cosmos, the heliocentric solar system. It was a bold idea. He sashayed out there, and he turned out to be right about that one. He turned out to be wrong about other things, smaller things to be sure. Most infamously, in what I've read, he was really wrong about what causes Earth's tides. That took Newton to start to identify what that really was. But Galileo had these bold ideas, and there are people, and that's just fundamental to the history of science, is that we have these. It just generally does not happen in the same person to have these big, bold, paradigm overturning ideas, and also the ability to pin them down, to really establish them, to really get them well-founded. And I hope in a future episode to talk about that in terms of what happened in mathematics in the 17th, 18th, and 19th centuries. So watching Galileo, though, so with many of his results about accelerated motion in the works that we're reading today, which are this funny dialogue we're reading this week, some pieces from the third and fourth day of a certain dialogue that was written late in his life, summarizing results from his earlier books that had been gotten themselves on the index, partly because Galileo was really good at insulting people, getting people irritated. And but you look at this methodology, and he's wading through. Some of his proofs are a little shaky, but most of them are, what they all are, is kind of tedious. Looking at these diagrams and reasoning about proportions between this line that represents time and this line that represents space. And he had the need also to wade through a whole bunch of cases. So he has 3 propositions where he basically does what we would do with algebra in a matter of, I would do them in a matter of seconds. Not everyone is enthusiastic about algebra as I am. But, they're not complicated. They don't need quite this level of brain bleeding reconsideration in order to be understood with modern notation. But they didn't have modern notation. They didn't have the idea of, I'll just multiply both sides of this equation by this figure, and that will clear that proportion out, and off we go. We're off to the races. They had to wade through these things as if they were somewhat, as if they were characteristically different. There's a parallel with what was going on in Italy in the 16th century. So really, people living certainly, well remembered in Galileo's time, far better than they are today. And also people who, were, intellectual direct, forebears to Galileo, people who were obviously affecting his educational environment. So they were wading through things like, what I'm most familiar with is the solution to the cubic equation. And there are figures named Tartaglia and Ferraro and Cardano, in particular, who are associated with the general solution to the cubic equation. So, if a quadratic equation has a square, a term, an x term, and a constant term in modern notation, a cubic equation has all of those and an x cubed term, which is a lot harder to solve in general, as you might imagine. You can, if you're lucky enough, you can solve it with factoring, because you can solve anything with factoring if you're lucky. But if you're not, then you need some, really powerful methodology, and it took until the 16th century for that to get invented. So, and then there's, and they're also hamstrung by, they have a very, they have the beginnings, because algebra is a word that's Arabic in origin, and so they had elements of that already. But it took a long time for our algebraic notation to come into existence, and so Galileo largely eschews it, and the Italian algebraists of the century before were using it, but they had no concept of like a negative number. So they couldn't simply move things back and forth across the equals sign. You have to wade through, if you're considering the case of, as they did, it was a stepping stone, the quote depressed cubic, which has no square term. It's fundamentally a different equation in some sense if you have the cube term and the linear term on one side and the constant on the other, because they all have to be positive, as opposed to having where all the coefficients have to be positive, as opposed to having all the numbers, as opposed to having all the terms on one side, as opposed to having the cube term by itself on one side. All these had to be weighted through as separate cases, and it was incredibly tedious. So this, the overturns that were coming in the 17th and especially the 18th century, because, to my knowledge, by the end of the 18th century with Leonhard Euler, we have our modern notation, most of our modern, the fundamental elements. And of course, as mathematicians continue to invent new concepts, we need new notation to express it. But yeah, so it's nearly in place by that point. But in Galileo's time, it's still very suspect, and Galileo doesn't use it at all. And it's also fascinating to look at what Galileo's trying to do in reasoning about motion, and looking at how close in this geometric paradigm he's coming to the idea of limits and infinitesimal quantities, and these sort of infinite sums of little, he calls them, he points out parallels. I draw this line, and then this represents time, and then along this line representing time, I draw all these perpendicular lines that are parallel to each other, so he calls them parallels. And they are representing the velocity, and it's going up in free fall. It continues to go up at a constant rate, and that was a major insight for Galileo. Once something has fallen 2 seconds, its velocity has doubled, not from after falling 1 second, as opposed to up to that point they would have said, a medieval physicist, if he bothered himself with such a quantitative question at all, would have said, well, after the distance it has, after a meter, it has, attained a certain speed, and after 2 meters it must have attained a doubled speed. And they had evidence for that, in the sense that impacts, if you, set yourself up a nice little sandy patch and drop things onto it, if you drop a ball from 2 meters, it makes, in some sense, twice as large a hole as the one at 1 meter. And of course, that was going to have to remain to be resolved, that what's going on there is kinetic energy, not velocity. Because they had no good way to measure velocity. So they could take a stop-motion camera and, take photographs of the dad blame thing as it fell. So they really, it's just fascinating. Looking at physics, that Galileo is groping to do, hamstrung by the equipment and hamstrung by the notation and intellectual equipment he has to bear on the problem. It's just fascinating. One last note, as I mentioned, the Italian algebraists and their solution to the cubic equation. So, so there's a sense that, it's obvious that the number -1 doesn't have a square root, right? That's obvious. You can't multiply 2 numbers together from the real world and get -1 or any negative number once you've allowed yourself the concept of negative number. And yet, when you look at the formula that was developed to solve the cubic equation in general, and then you look at cubic equations, which, quadratic equations can have no solution. There are quadratic equations that have no roots. The parabola, in a graph, in analytic notation, the graph simply never crosses the x-axis, so it has no roots, it has no solutions. But a cubic equation always has to. The nature of it is it's going up on one side and it's going down on the other off to infinity, and it does a couple bends in the middle usually, but it always has to cross the x-axis. And yet when you use the Cardano formula on many cubic equations, you wind up with, the square root of -1 inside there. And you realize you have to just carry on and pretend that it's a number you can work with and do a little mental gymnastics. It's like, well, if I allow I equals the square root of -1, well, what happens if I cube that? Oh, well, it's negative I. All right, well, I need to find the cube root of negative I, so I guess that's I. Off we go. So this was, this new notation that was going to open up, and there was a new freedom of we're just going to follow these concepts as far as they're going to go. So next time I really want to, that's kind of a segue to the next time that I, this little series, which might be 2 podcasts, maybe longer. That would be the point of departure probably for the next time. So, all right. Well, I hope you were all well. I know that in the world outside of Wyoming, things are crazy. New York is flooding. Delta variant, all of that good stuff. It's smoky here. We keep putting off our astronomy field trip for my field science class because there's just too much smoke in the air coming from, hundreds of miles away. It's a strange and uncertain world we live in. It's kind of amazing that there are that many regularities that we can tease out as we can in physics. So, with that little meditation, that, the details are uncertain, and yet the big picture is very certain. I'll leave you to it. God bless.
Thanks for listening to this episode of That's So Second Millennium. TSSM's audio producer is Morgan Burkhardt. Our theme music, Igneous Grok, was composed and performed by Vin Marquardt. For my co-host Bill Schmidt, I'm Paul Giesting. Until next time.